So let's do some questions. The first question of the exercise is magnetic intensity H at the center of a long solenoid carrying a current of 2 ampere is 1500 ampere per meter. We need to find the number of turns per centimeter of the solenoid. So this is the first question. We know that for a solenoid, magnetic field intensity is given by this formula, and magnetic field intensity and magnetic intensity is B over mu naught. Magnetic intensity is B over mu naught. So H will be equal to mu naught Ni over mu naught. So H will be equal to N into I, where N is the number of total number of N is the number of turns per unit length and I is the current. So first of all, it is given to us that H is 1500 ampere per meter. Now N is unknown and current is given 2 ampere. So from here N will be equal to 1500 over 2, that is 750 turns per meter. So N will be 750 turns per meter, and if you want to find in centimeter, N will come out to be 7.5 turns per centimeter. In question 2, there is a rod inserted as the core in the current carrying solenoid. In the previous question, we need to find the magnetic intensity at the center, and if magnetization I is given, then we need to find the susceptibility, and if this material paramagnetic, diamagnetic or ferromagnetic. So this is the second one. The first part is, it is given that H will be 1500 ampere per meter, because we have to use the data of the previous question. So as this solenoid and rod are long, we are only interested in the magnetic intensity at the center. At the ends, the effects may be neglected. So there is no effect of the rod on the magnetic intensity at the center. So magnetic intensity will remain same. It will remain same. There will not be any effect of the rod. Let's say there is a rod, so there will not be any effect of this rod at the center of the solenoid. We are not discussing about the ends, remember, because it is a long solenoid, so it will remain same. Now we need to find susceptibility. Susceptibility is I over H. So I is 0.12 and H is 1500, so it will be 8 into 10 to the power minus 5, and susceptibility is unitless. Then is this what is this material? So this material is paramagnetic. This material is paramagnetic. So by looking at this value, we can say that this material is paramagnetic. In question 3, we have a magnetic field inside long solenoid having 50 turns per centimeter. It increases from some value to some other value when iron core is introduced. Now we need to find the current in the solenoid and the magnetization I and the pole strength. So this is the third one. So first of all, what we have, the initial magnetic field is 2.5 into 10 to the power minus 3, and final magnetic field is 2.5, both in Tesla. Area is 4 into 10 to the power minus 4 meter square. Number of turns per unit length is 50 turns per centimeter, or 5000 turns per meter. So first part, we need to find the current. So by using this formula for the solenoid, so 2.5 into 10 to the power minus 3 equal to 4 pi into 10 to the power minus 7 into 5000 turns per meter into I. So from here current will be 0.398 ampere or approximately 0.4 ampere. B part. Now we need to find I, so it can be founded by B2 over mu naught minus H. So 2.5 over 4 pi into 10 to the power minus 7 minus H is B2 minus B1. So I equal to 2.5 over 4 pi into 10 to the power minus 7 minus 2.497, the difference between these two magnetic fields. So it will be 1.99 into 10 to the power 6, approximately 2 into 10 to the power 6, and unitless. Then I can be m over v. This magnetic dipole moment can be magnetic strength into length over area into length. Volume can be area into length, so it can also be magnetic pole strength over area. So m will be I into area, so it will be 2 into 10 to the power 6 into 4 into 10 to the power minus 4, which will give us 800 ampere meter. In question 4, we have a bar magnet of length 1 centimeter and some cross section area. We need to find magnetic moment, and we need to find the magnetization, and we need to find the magnetic field at the center of the magnet. So this is the fourth one. So what are the things that we have? So first of all, distance 0.15 meter, length 1 centimeter or 0. Or you can say 1 into 10 to the power minus 2 meters. This can also be written like 15 into 10 to the power minus 2 meters. Then area is 1 centimeter square or 1 into 10 to the power minus 4 meters square. Magnetic field intensity 1.5 into 10 to the power minus 4 Tesla. So we need to find m. So using the formula, this is for the actual position. So 1.5 into 10 to the power minus 4 equal 10 to the power minus 7 into 2 into m into 0.15, or you can also write 15 into 10 to the power minus 2 over 0.15 square is 0.0225 minus 0.0001 whole square. So from here m will be 1.5 into 10 to the power minus 4 into 5.01 into 10 to the power minus 4 over 3 into 10 to the power minus 8. So m will be approximately 2.5 amperes. Ampere per ampere meter square. Now the second part, magnetization I, which is m over volume. So 2.5 over 10 to the power minus 4 into 10 to the power minus 2, area into length. So 2.5 into 10 to the power 6 ampere per meters. Then H is equal to m over 4 pi r square or 4 pi d square. So m over 4 pi I d square. So it will be 2.5 into 4 into pi into 0.01 into 0.15 whole square, 0.15 square. So after solving this, we will have net magnetic intensity due to these two things, 0.4, so 8.846 into 10 to the power 2. B will be mu naught minus h plus I. So 4 pi into 10 to the power minus 7, 2.5 into 10 to the power 6 minus 2 into 884.6. So it will give us approximately 3.14 Tesla.